Curves in industrial design, polynomial curves and the Bernstein basis. Polynomial parameterizations. A line segment is often parameterized as a degree 1 polynomial in the form a0 plus a1 times t, and we've chosen t to be between 0 and 1. When parameterized in this way, the line segment passes through a0 when t equals 0, and a1 gives the direction of the line segment. The same line segment can be parameterized as a degree 1 polynomial curve in this manner. To be the same line segment, C0 has to be A0 and C1 has to be A0 plus A1. Parameterized in this form, each point of the line segment is given as a barycentric combination of the points C0 and C1. And the line segment starts at C0 when t equals 0 and ends at C1 when t equals 1. The same kind of parameterizations we can have with parabolas, which are polynomial curves of degree 2. A parabolic arc can be expressed in this manner, where we have chosen t to be between 0 and 1. When expressed in this way, the points on the parabolic arc are not barycentric combinations of a0, a1, and a2. And the arc passes only through the point a0 when t equals 0. The same parabolic arc could be given as a barycentric combination of points. To be the same parabolic arc, a0 and c0 are equal, and c1 and c2 can be given in terms of a0, a1, and a2. With this parameterization, the parabola passes through the points c0 when t equals 0 and c2 when t equals 1. Notice that this is a barycentric combination because this number plus this number plus this number add up to 1, and these three numbers are positive when t is between 0 and 1.
The screen, we can see on the left the same curve than on the right. These are the same curve. Here is written in terms of C0, C1, and C2, and on the right is written in terms of A0, A1, and A2. When we move A0, we see how the curve moves. It translates with this A0. When we move A1, the curve also moves in not a very intuitive way, and also when we move A2. Now, if we move C0, the curve moves with C0. It follows C0. When we move C1, the curve also follows basically the position of C1, although it's not on C1. C1 is not on the curve. And finally, when we move C2, the curve also follows the point C2. So geometrically, it's easier to know how the curve is going to be described by these coefficients, C0, C1, and C2, than these coefficients, A0, A1, A2.
The points on the quadratic curve, parameterized in the way we described before, in this manner, are barycentric combinations of the points C0, C1, and C2. Here we see an example of a parabolic arc parameterized in this way. And these are the points C0, C1, and C2. These points are called control vertices. The ordered set C0, C1, and C2 is called control polygon of the curve, and is usually represented using the edges that join C0 to C1 and C1 to C2 in that given order. Since the points on the curve are barycentric combinations of the points C0, C1, and C2, the curve is contained in the triangle with vertices C0, C1, and C2, that is, the convex hull of those points. Bernstein basis of degree 2. So we now are going to define what a quadratic Bezier curve is. A quadratic Bezier curve is a polynomial curve of degree 2 parameterized in this particular way, for t between 0 and 1. These numbers are the Bernstein polynomials of degree 2. This is the first Bernstein polynomial of degree 2, this is the second Bernstein polynomial of degree 2, and this is the third Bernstein polynomial of degree 2. Here we see a picture of the first Bernstein polynomial of degree 2 between 0 and 1, the second Bernstein polynomial of degree 2, and the third Bernstein polynomial of degree 2. We can see that for t between 0 and 1, these polynomials are positive. So a Bezier curve is given in terms of the basis of the Bernstein polynomials of degree 2 and the coefficients C0, C1, and C2, which are the coefficients of the Bezier curve with respect to the Bernstein basis. A cubic arc expressed in this way for t between 0 and 1 is not a barycentric combination of a0, a1, a2, and a3, and it only passes through the point a0 when t equals 0. The same cubic arc can be written as a barycentric combination of points c0, c1, c2, and c3, where these points can be given in terms of the datas a0, a1, a2, and a3. In this case, it's a barycentric combination of points because these numbers add up to 1 and they are positive for t between 0 and 1. When t equals 0, the curve passes through the point c0, and when t equals 1, the curve passes through the point c3. The points on the cubic curve, given in this particular way as we described before, are barycentric combinations of the points c0, c1, c2, and c3. Here we see the cubic curve and the points c0, c1, c2, and c3. These points are called control vertices. The ordered set c0, c1, c2, and c3 is called control polygon of the curve and is usually represented using the edges that join c0 to c1, c1 to c2, and c2 to c3 in this order. Because the points of the curve are barycentric combinations of the control vertices, the curve is contained in the convex hull of the control vertices, as we saw here. This is in blue, we can see the convex hull of the control vertices. So, a cubic Bezier curve is a polynomial curve of degree 3 parametrized in this particular manner, as we have described before, for t between 0 and 1. These numbers here for t variable are the Bernstein polynomials of degree 3. This is the first Bernstein polynomial of degree 3. This is the second Bernstein polynomial of degree 3. This is the third Bernstein polynomial of degree 3. And this is the fourth Bernstein polynomial of degree 3. Here we can see a picture of the first Bernstein polynomial of degree 3, the second Bernstein polynomial of degree 3, the third Bernstein polynomial of degree 3, and the fourth Bernstein polynomial of degree 3. These Bernstein polynomials form a basis, the Bernstein basis of degree 3. And the points in the control polygon are the coefficients of the Bezier curve with respect to the Bernstein basis. In general, the Bezier curve of degree n is a polynomial curve of degree n parametrized in this way, as a combination of the control vertices c0 to cn and the Bernstein polynomials of degree n. The control polygon of a Bezier curve of degree n has n plus 1 control vertices. And the Bernstein basis of the Bernstein polynomials of degree n is this Bernstein basis with n plus 1 polynomials. Each polynomial is of this form: a binomial coefficient multiplied by 1 minus t, in this case to the power n minus k, times t to the k, for k an integer, a natural number between 0 and n.